Hi, so for today we're going to talk about variable separable DE. Okay, so this is a next topic when you are already done with families of curves, and we're going to solve some problems involving variable separable DE. I have here about 8 examples so that we could at least master the solution of a variable separable DE. Now, what is a variable separable differential equation? So we can say that a D is a variable separable if all terms containing x can be grouped with dx and y can be grouped with the dy. So all terms containing x and y must be grouped with dx and dy respectively. So if we can group the functions of x with dx and the functions of y with dy, then the d is said to be variable separable. So we have two types of solutions. Okay, so number one, we have the general solution and a particular solution in D. So, yeah, general solution, a solution that contains arbitrary constants. However, those arbitrary constants or this arbitrary constants is not yet defined. In our previous discussion of differential equations, our main goal in the families of curves and in the elimination of arbitrary constants, we need to come up with a differential equation that does not longer contain, okay, an arbitrary constant. Here, in the solutions of differential equations, such as variable separable differential equations, we're going to come up with a constant. Okay, and that constant is actually can be defined and not yet defined. So if the constant is not yet defined or its value is unknown, that is what we call the general solution. Okay, we have here the particular solution. So particular solution, a solution that no longer contains arbitrary constant, meaning the arbitrary constant now here are defined. It means that it has already a value. You have already computed for the value given a certain condition in the differential equation. Okay, so again, if we are solving differential equation, our goal here, okay, is to eliminate the dx and dy. So, in our families of curves and arbitrary constants, again, we need to eliminate the constant. Here, our answer should have constants, and we have to eliminate the dx and dy, or actually the derivatives. Okay, so let's get started. So for number one, solve the DE by separation of variables. Okay, so this is a very easy example. Okay, we know that class that we have dy over dx, y prime is equals to dy over dx, and that is equivalent to 2y over x. Okay, separation of variables, separable DE says that if we can group all the dy's into the y and all the dx into the x, okay, that is said to be a variable separable DE. So, if I'm going to cross multiply these two, so what will happen? I will have dy over 2y is equals to now dx over x. As you can see now here on the left side of our equation, dy of our function of y, okay, all terms of y is grouped into dy. Okay, and all functions of x are now grouped into dx in this example. So, what are we going to do here is, in order for us to get the solution upon grouping these variables into its certain or into its respective y, dy's, and dx, what are we going to do next is, actually, we're going to integrate both sides of the equation. Okay, that's right. So upon integration, we all know that whenever we perform integrals, there is always a plus constant. So that is what we are trying to do here. Okay, so we know that if we integrate this, we can factor out 1/2 because that is a constant outside of the integral sign. We have dy over y, and we have the integral of dx over x. Okay, so if we integrate dy over y, that is simply ln of y. Okay, and the integral of dx over x is simply what? Ln of x plus the integration constancy. So, in our study of variable separable, we can choose where we are going to write c. But actually, we can always attach this into one of those integrals, plus c. Okay? So, how do we solve this? So, actually, continuing this by properties of logarithm, we can multiply, okay, we can multiply both sides by 2 to cancel the 1/2. So we have ln of y is equals to 2 ln of x plus twice the c, okay, 2 times c. Remember here in DE, the constant twice a constant, still we can label it as still the c, because twice the constant is still the constant. Okay? So, and we know, class, that by the properties of logarithm, this 2 ln x can be written as ln, okay, oops, ln ln of x squared. So whatever the coefficient here, you can always rewrite it as the exponent inside the logarithmic sign. So we have plus c. Now, our main goal, since both the y and both the x are in terms of ln, I could simplify them by, I could eliminate the ln sign, the natural logarithm sign, by actually what? Raising them both into e. Okay? Both sides of the equation. So whatever you do on the left side of the equation, definitely you're going to do on the right side of the equation. So that e raised to ln, this would be cancelled, and the left side of our equation will simply be y. Okay? Will simply be y. That's a property when we raise ln to e. So whatever it is inside the ln, that would be the result. Okay? And here, by properties of exponent, we have e ln x squared plus multiplied by e raised to c, because here we have an exponent, okay, that is plus. So if we can decompose this, it should be this, because we have the same base. By loss of exponent, if we have the same base, we can add the exponent. So I've actually broken it into pieces. So for our discussion, okay, so for the sake of our discussion, we're going to cancel this again, and our result will be x squared multiplied by e raised to c. But e raised to c is still simply equal to the constant itself. So, in other words, we have an answer that is equivalent to y is equals to cx squared. So, here we have already solved the variable separable DE, which contains arbitrary constant C, but the constant C is not defined. So, hence, this is a general solution, okay, of the variable separable DE. Okay, this would be our answer. Y is equals to CX squared. Okay, so for our next example, so for number 2, we have 2x times y plus 1 dx minus y dy is equals to 0. At a given condition at x is equals to 1 and y is equals to 0. So if we have a condition, then definitely we should be able to come up with the general solution of the DE, as well, of course, the particular solution of the DE. In the previous example, we don't have any conditions, so we only get the general solution of the DE. But here we have already this condition at x is equals to 1 and y is equals to 0. Definitely we can get the particular solution. So first things first, we need to separate this term, okay, and group this into dy. And also, of course, what are we going to do? Group first, okay, the d's. So we have, if I'm going to multiply this or divide this both sides of the equation by 1 plus y plus 1, then definitely this would be cancelled. This would be 2x over dx. So let me just write so that you would see, okay. So this would be cancelled, okay? And we are left with 2x dx minus, okay, y dy over y plus 1. is equals to 0. So here is our, we already group into dx, and all terms containing dx and all terms containing dy are now grouped with the y. So the next the next step is actually, again, to integrate. Okay, so what will happen, I will just rewrite this as this: 2x dx is equals to y dy over y plus 1. Okay, if I'm going to integrate both sides of the equation, okay, so what will happen is, we will be canceling those dx and dy, and we will be able to come up with the integration or the constant. So we have 2 by properties of integral, okay, and we have the integral of y over y plus 1 dy. Okay, so how do we integrate the left side? So it's very easy. So we know that this should be x squared over 2. This would be cancelled, and still we are left to find the integral of y over y plus 1 dy. So we have x squared here. Okay, so how do you find the integral of this? Okay, how do you find? So it's advisable that to find this integral, you can also use substitution, but that is not my method. But also you can use that. But for me, you can actually rewrite this integral as what? We have 1. I'm going to make the numerator the same as the denominator. So if I'm going to add plus 1 also here and group it with this, and I'm going to minus 1, add minus 1 here, over y plus 1 dy, this numerator is still the same as y. Okay, because y plus 1 minus 1 is still equal to y. And I'm going to, what? Apply the rules or properties of integral. I could separate them, okay, and evaluate their integral, okay, such that I have this. So we have already separated this and this, okay? So we can only separate numerators, not denominators, right? So this would be cancelled. So the integral of simply dy will become y, that's right, minus, and the integral of this, now this is still ln, because if you make u as y plus 1, you make du with respect to dy, okay, this would be 1. So du is simply equal to dy. So if you're going to substitute here, the u's here, so what will happen? We have dy is equals to du over simply u is equals to y plus 1, which is u. So du over u, if we get the integral of that, okay, if we get the integral of that, simply that is, yes, ln of u. Okay, but u is equal to, again, u is equal to y plus 1, so we need to get it, we need to back substitute. So we have, upon integration, we have the constant c, of course. And as you can see here, yung dx does not have any natural logarithm. So better yet, leave this as it is. Okay? We cannot cancel the ln here. So this would be our general solution. Okay? General solution. So, general solution again, a solution that contains arbitrary constant, but the arbitrary constant here is not defined. So we need to find the value of c, because we are given the equation or the condition that at x is equals to 1, y is equals to 0. So we have the condition at x is equals to 1, y is equals to 0. So what are we going to do? Simply substitute. We have 1 squared is equals to 0 minus ln of 0, y0 plus 1 plus c. So as you can see here, ln of 0 or ln of 1 is simply 0 also. So in other words, 0 minus 0 plus c, then c is equals to 1, because 1 squared is equals to 1. And hence, if we're going to get the particular solution of this differential equation, we're going to substitute the value of c to our general equation. So hence, therefore, our particular solution will now be x squared y minus ln y plus 1 plus 1. Okay? So this should be our particular solution. Hence, it contains no arbitrary constant because the constant here is defined. So this is now the particular solution. Okay, let's solve another example. So we have for number 3, we have 2xy prime is equals to 1 plus y squared at a given condition x is equals to 2, y is equals to 3. Okay, so first things first, we need to group them in terms of dy and dx. So we have 2xy, y prime is equal to simply dy over dx is equals to 1 plus y squared. And if we cross multiply dx to the both sides of our equation, so we have 2xy dy is equals to 1 plus y squared. We have dx here. And we need dy here. We need all terms of y to be in here and all terms of x to be in here. So hence, if I'm going to divide them both sides by, let's say, I would like to divide it by, let's say, 2x, because I want to cancel 2x here, and I need to have 1 plus y squared here. So I would like to cancel here, cancel this here. So what will happen? We have an equation that is y dy over 1 plus y squared is equals to, we have dx over 2x. Okay? So, hence, we group all terms of y in dy, all groups of x in dx. So, the next step again is to integrate both sides of our equation. Okay, and upon integrating, we shall arrive, or we shall eliminate the dy and dx here. So, we have here, okay, integral of, let me just rewrite, y squared plus 1, okay, dy, and we can factor out 1/2 outside of the integral sign again, so that this is dx over x. Okay, so how do we integrate this? So here we can use the u substitution. If we left u as y squared plus 1 and du with respect to y is 2y dy, so I have an available here of y dy. This is my y dy. Okay, but I have to offset 2 here because the du is actually 2y dy, but I have also have to correct it by a correction factor outside of the integral 1/2. So whatever it is that you multiplied inside of the integral just to satisfy this du, you're going to get the reciprocal of that and again add it or multiply it outside of the integral. So in this case, we added 2 to satisfy this, to perform u substitution, and the reciprocal of this is 1/2. So you're going to multiply it 1/2. That is the correction factor. So that I would be able now to write this as the integral of 2y dy. 2y dy here is simply equal to du over, what is our u? Y squared plus 1 is u. So over u. And again, equal to 1/2 dx integral of dx over x. So this is both our logarithm. So we have 1/2 ln of u, okay, is equals to 1/2 ln of x plus c. But we need to substitute back u to its original substitution. So we have ln of y squared plus 1 because u is equals to y squared plus 1 is equals to 1/2 ln of x plus c. As you can see, both of the x and dy contains ln. So we can multiply both sides by 2 so that we can eliminate 1/2 here. So that we have ln y squared plus 1 is equal now to ln of x plus c. That should be our result. And in order for us to eliminate the ln, again, what we did a while ago is we need to raise this both sides of the equation with e. So y squared plus 1 is equals to e ln of x plus c. So this should be cancelled, okay? And whatever left inside of the ln, that should be our result. Y squared plus 1 is equal now to, by loss of exponent again, I can decompose it into this, okay? Because of by law of exponent, this is equal to this, okay? So what will happen? Y squared plus 1 is equal now to, this should be cancelled. So simply x multiplied by e raised to c, okay? And again, e raised to c, this term is simply equal to, that's correct, simply equal to c, simply equal to c multiplied by x. So this should be our what? We have an arbitrary constant of c. So this should be our general solution. General solution. Okay. Let me just rewrite. So we have the general solution. Okay. But we have a condition. A condition is x at x is equals to 2 and y is equals to 3. So definitely we need to find the value of the c in order for us to satisfy the condition. That's a particular solution. So at x is equals to 2, that is 2 squared plus 1 is equals to, that is not 2, that is simply 3 because our value of y here is 3. So 3 squared plus 1 is equal to c times 2. Okay? So this is 10. 3 squared is 9 plus 1, 10. We have 2c here. So c is therefore 5. So again, to get the particular solution, simply substitute the value of c on our general solution. Okay? So we have y squared plus 1 is equal now to 5x. So this should be our particular solution. Okay, so for another example, so we have number 4, still a variable separable DE. We have x cubed plus 2, y is equals to x, y raised to 4 plus 3, y prime, at a given condition that x is equals to 1 and y is equals to 1. So again, same first step. We need to express we need to group dx and dy with x and y respectively. So we have this y prime is simply equal to dy over dx. So multiplying both sides of the equation by dx, we have x cubed plus 2 y dx is equals to x y raised to 4 plus 3 dy. And if I'm going to divide the whole side of our equation by y, because of this we need to eliminate this, and here with x, y over x, so simply what will happen is we have x cubed plus 2 over x dx is now equal to y raised to 4 plus 3 dy, okay, over y. And upon grouping them, the very next step is again to integrate both sides of our equation so that we need to have, or we can eliminate dx and dy. So upon integrating, this integral can be simplified as we have x cubed over x dx. We can always distribute the integral sign if we have some or minus here, okay, and the dx of course plus 2. I'm going to bring this outside of the integral because it's constant. So we are left with dx over x. And that is equal to the same process, y raised to 4 over y, plus bringing out 3 here because it's constant. So we have dy over y. And we can simplify this by, this should cancel. This should be x squared. Okay? This should cancel. This should be y cubed. And proceeding to our integral, now we have the integral of x squared dx plus 2 integral of dx over x, integral of y cubed plus 3 integral of dy over y. So integral of x squared dx, that is 1/3 x cubed plus, this is ln again, 2 ln of x is equals to 1/4 y raised to 4 integral of y cubed plus 3 ln of y, don't forget the plus c. Okay? Again, since both here we have an x term that is in terms of logarithm and we have an x term that is not in logarithm, okay, we cannot cancel out easily the ln. Okay, here, the same here. We have 3 ln y and the other one is in this form. So we cannot cancel. So we can leave it as it is. So therefore, this is our what? General solution. But take note that we have a condition, and that condition is at x is equals to 1, okay, and y is equals to 1. So we simply substitute the values 1/3, 1 cube plus 2 ln of 1. This is 0, simply 0, because ln of 1 is 0. Is equals to 1/4, 1 raised to 4, plus 3 ln of 1. This is simply 0. ln of 1 is 0. Plus c. So as you can see, 1 cube is still 1. 1 raised to 4 is still 1. 1/3 is equals to 1/4 plus c. We need to find c. c therefore is 1/3 minus 1/4. Okay, so what will happen here? 4 minus 3 over 12 is 1 over 12. So our value of c is 1 over 12. Hence, therefore, our solution or particular solution will be 1/3 x cubed plus 2 ln of x equals to 1/4 y raised to 4 plus 3 ln y plus 1 over 12. So this is our particular solution for this problem. Okay? So, as you can see, differential equation, solving differential equation, okay, first we need to group in terms of dy and dx. That's when the differential equation part is done, okay? The next step is to integrate. Again, integral calculus is essential. And after integration, algebra part is essential also. Okay? Okay, so next problem, the only way for you to be good or to master your mathematics subjects is none other than solving many problems as you can. So in this video, I always give many examples for the viewers to really practice their skills. Okay, so there is no other way for you to be good at math rather than solving many problems. Okay, this is a variable separable DE, and we can simply what separate it e raised to 2x dx by simply multiplying or dividing both sides of the equation by y, and for y multiplied by 4 plus e raised to 2x, so that we have 4 plus e raised to 2x here, and we have, of course, dy over y here. So again, upon grouping them, we need to integrate both sides of our equation for us to find the constant, okay, or the general solution. So how do we integrate this? As you can see here, this integration involves u substitution. Why? Because this, if we let that as u, okay, 4 plus e raised to 2x, if you get the derivative of u with respect to x, that is simply 0 plus 2e raised to x. Cross multiplying the dx here, we have du is equals to 2e raised to 2x dx. And e raised to 2x dx is this. Okay? But again, upon differentiating, we have 2 here. So we have to offset 2 here. Offsetting 2 here, we should offset outside of the integral 1/2 for our correction factor. And hence, we can now perform the u substitution. So we have 1/2 integral of 2e raised to 2x, 2 times e 2x dx is simply equal to du over 4 plus e 2x, that is simply du. Okay? Integral of dy over what? So this is pretty much easy. So this is still ln of u is equals to dy. Integral of this is ln of simply y plus c. Don't forget the plus c. Okay, and of course, we need to back substitute u as this 4 plus e raised to 2x is equals to ln of y plus c. We can multiply both sides of the equation by 2 to eliminate 1/2 here. So we have ln 4 plus e raised to 2x is equals to twice the ln of y plus c. So we have ln 4 plus e raised to 2x is equals to 2 ln of y plus 2 times c is still c by properties of logarithm, we can rewrite this 2ln y as ln of y squared plus c. Okay, in order for us to eliminate ln, because we have ln in terms of x, ln in terms of y, we can again raise them up, okay, by e. So we have ln of y squared plus c. So this should be cancelled. So whatever left is the answer for that. 4 plus e raised to 2x is equals to, this can be written as, this side can be written as by loss of exponent again as this. So we have 4 plus e raised to 2x cancelled. So we have y squared. E raised to c is simply equal to c. So we have an answer that is 4 plus e raised to 2x is equal to cy squared. Okay? This should be our general solution since we are not given any condition in the problem. So sometimes you will eventually see some answers in differential equation that the term c or the arbitrary constant c is raised to squared, cube, sometimes 2c, but I haven't seen like that before. So if you encountered c squared here instead of c, that is still correct answer. That is still a correct answer. Okay? The c here is actually what? The c squared, it doesn't matter. Where this c is raised to or twice a number or thrice a number, it is still c at the end of the day. Okay? So if you see an answer of c squared, y squared in this, for this example, okay, because if we solve it in another way, we will be ending up with c squared. Okay? So, but still, that c squared is equal to a constant c. Okay? Let's try to solve another problem. Okay? So, let's try. Let's try this. Number 6, we have my dx is equals to nx dy. So as you can see here, uh, m and n are actually constants because we are concerned with integrating the in terms of dx and dy. So any variables rather than x and y are considered as constant. So in this case, so we can what? We have m dx. We need to get x. So over x is equals to n dy over, we need to get y here. So this would be our equation. If we group them in terms of x and in terms of y, note that m and n are constant. So we have to integrate both sides of our equation. And then upon integration, we can rewrite this as m dx over x. Because m is constant, we can move it outside of the integral sign. And n integral of dy over y. So that we can integrate now m ln of x is equals to n ln natural logarithm of y plus c. And by properties of natural logarithm, this can be written as ln of x raised to m, okay, is equals to ln of y raised to n plus c. Upon eliminating again the ln, we need to raise them as ln x raised to m is equals to e natural logarithm y raised to n plus c. And of course, this should be x raised to m. And we know what will happen to this. So e ln y raised to n times e raised to c by properties of exponent. And again, this should be cancelled. X raised to m, okay, is equal now to y raised to n, okay, c multiplied by c. Or in other words, to look it nicer, for it to look it nicer, that your answer, x raised to m is equal to c y raised to n. So that should be our general solution since we don't have any condition set in our problem. Okay? So for number 7, let's try to look at this. Number 7, x a cosine squared y dx plus tangent of y dy is equals to 0. Okay. So still we need to group them in terms of x for dx, y for dy. So as you can see here, this is the problem, cosine squared of y. So we need to get it here. So we have what? We can multiply or divide both sides of the equation by 1 cosine squared of y. So what will happen? We have x dx plus, okay, tangent of y over cosine squared y. Let me just rewrite this, okay? Okay, so we have dy here is equals to 0. And again, we need to integrate. Okay, integrate. So what will happen here is that we have x squared over 2, okay? Plus, as you can see here, this is an integral by property or by trigonometric identity, 1 over cosine squared of y is equivalent to what? Okay? If 1 over cosine theta is equal to secant theta, then this whole equation or this identity is now equal to what? So this is 1 half x squared equal to secant squared theta plus integral of secant squared y, because our function here is y. Okay, our function here is y. So we have secant squared y, okay, times tangent y dy is equals to 0. So how do we integrate this? How do we integrate this? We can integrate this by letting u as what? So in order for us to integrate this, we need to let u as tangent y. Du with respect to y is secant squared y. Du is now equal to secant squared y dy, which is available on our integrand. So we have 1 half x squared plus, okay, the integral of, again, tangent y is u. Secant squared y dy is equivalent to du equals to 0. So we have 1 half x squared plus u squared over 2, again, plus c is equals to 0. And we need to back substitute whatever the value of u, okay, plus what is u squared? This is u is our u, tangent y. So it is now raised to 2, okay, over 2 plus, again, constants of integration is c. We can multiply this equation by 2. We can cancel out 1 half, so that we have x squared plus tangent of y squared plus 2 times c is still c is equals to 0. And if we're going to distribute this, we have x squared plus tangent of squared y plus c is equals to 0. So this should be our general solution for our problem, for this problem. Okay, down to our last example for this video. So we have x plus 2 dx is equals to x plus 3 sine of y cosine of y dy. First step, again, group them in terms of x and dx, y to dy. So we can eliminate x plus 3 here because this is purely y. So we have x plus 2 by over x plus 3 dx, and this is now sine of y cosine of y dy. And we can now what? Integrate. Okay? So as you can see here, how to integrate this first. So one factor is that we can always make the numerator the same as the denominator, given that if we are only have to add constant, we cannot add x terms here or y terms here. So I'm going to rewrite this equation as x plus 3, okay, x plus 3 minus, okay, let's say x plus 3 here this should be x plus 3 minus 1. So we have dx, okay, and integrating this sine of y, cosine of y, dy. So this is this sine of y and cosine of y has a relationship with each other. So that if we let u as equal to sine of y, then the du with respect to dy is cosine of y. Cross multiplying, we have du is equals to cos y dy, which is readily available. So this is simply a u substitution, but in here we can still what? Perform the property of integral, wherein we can substitute or distribute, I mean, the integral and dx sign. So we have minus dx over x plus 3, and that is equivalent to the integral now of, if we let u assign y u, then du. Okay, so we can see here that this should cancel. So what will happen? We are left with dx minus, okay, if we let u here as x plus 3, du with respect to x is 1. Okay, multiplied by dx is simply dx. So simply you are left with this dx or du over u is equals to integral of u times du. Okay, so here simply this is still ln, okay, because u over du over u. So what will happen? We have what? Integral of dx is x minus ln of u. This is u squared over 2 plus c. But u here is equal to x plus 3. And the u here is equals to sine of y. So we have now x minus ln of x plus 3 is equal to sine of y squared over 2 plus c. So this should be our answer, okay, for our last problem. This is a general solution since we are not given any condition. Okay, so that's all. Thank you so much for viewing my video. So this is Engineer Abat. This video is all about the variable separable D, and I hope you learned something today. Thank you so much, and God bless you.